Part 4. Membrane Composition and Imbalance. Chapter 11. How Modern Diet Disrupts SPM Production. Modern diet disrupts specialized pro-resolving mediator production not because it contains one single catastrophic ingredient, but because it gradually rebuilds tissues into a state that is better equipped for initiation than for completion. That shift happens through several overlapping mechanisms at once. Membranes become overloaded with omega-6, rich polyunsaturated substrate relative to omega-3 derived precursor pools. Oxidative burden rises, making highly unsaturated membrane lipids more fragile and less stable as signaling reservoirs. Mitochondrial strain increases, reducing the energetic capacity required for cleanup and tissue restoration. Barrier integrity weakens, feeding repeated inflammatory triggers into tissues that should already be transitioning out of defense. Enzymatic pathways remain crowded by initiation-heavy substrate traffic. The result is not merely more inflammation. The result is poorer inflammatory sequencing. The body still knows how to mobilize arachidonic acid-driven early-phase chemistry, but becomes less able to derive strong, sustained, downstream pro-resolving output from EPA and DHA when the moment for resolution arrives. One of the central distortions comes from the repeated dominance of linoleic acid-rich industrial seed oils and ultra-processed food systems that supply omega-6 substrate in quantities and contexts far removed from the slower, more structurally balanced patterns under which membranes maintain better signaling proportion. The issue is not that omega-6 itself is illegitimate. The issue is chronic overrepresentation. When tissue phospholipids are built in an environment saturated with omega-6 input while omega-3 incorporation remains comparatively weak, the membrane reservoir shifts toward early-phase inflammatory potential. More of the stored substrate pool is prepared to become arachidonic acid-heavy, eicosanoid, signaling once phospholipids are activated. Less of that pool is available for meaningful downstream conversion into resolvins, protectins, and maresins. This is how diet changes future inflammatory behavior long before symptoms become obvious. It alters the stored material from which later phases of the inflammatory sequence must be built. At the same time, the modern diet does not only distort substrate balance, it also destabilizes the environment in which omega-3 derived resolution signals would need to be generated. Highly processed foods often combine unstable polyunsaturated fats, refined carbohydrates, repeated glycemic load, low micronutrient density, poor antioxidant support, and flavor architectures that encourage chronic overconsumption. That creates oxidative and metabolic conditions hostile to clean resolution biology. A membrane containing EPA and DHA is valuable only if it can preserve those molecules long enough to use them intelligently. In a diet that repeatedly raises oxidative stress and postprandial inflammatory burden, highly unsaturated membrane lipids are exposed to a harsher chemical environment. They become easier to peroxidize, easier to damage, and less reliable as protected precursor stores for specialized pro-resolving mediator production. The diet does not just reduce omega-3 status quantitatively. It degrades the qualitative environment required for omega-3 to function as resolution substrate. Another major problem is the collapse of food structure into chronic inflammatory signaling. Refined carbohydrates, liquid sugars, emulsified fat-sugar combinations, and hyperpalatable ultraprocessed formulations alter insulin dynamics, adipose signaling, hepatic lipid handling, and postprandial immune behavior in ways that keep tissues biochemically louder than they should be. This matters for SPM production because the resolution phase depends on a body that can change phases. A body repeatedly pushed into glycemic volatility, lipotoxic overflow, hepatic stress, endothelial irritation, and adipose-derived inflammatory signaling remains too occupied with ongoing initiation pressure to hand off cleanly into the later logic of repair. Even if EPA and DHA are present, downstream conversion into pro-resolving mediator families may remain functionally weak because the organism is constantly being re-triggered into the front half of the inflammatory program. The problem is not just lack of substrate. It is chronic interruption of the phase transition required for that substrate to matter. Modern diet also damages SPM production through micronutrient dilution and structural insufficiency. Resolution is not driven by fatty acid alone. Enzymatic conversion, membrane protection, mitochondrial function, antioxidant defense, and immune cell phenotype shifts all depend on a broader nutritional context. A diet built from refined calories and chemically simplified food products can provide plenty of energy while providing poor support for the systems that protect membranes, manage oxidative stress, maintain metabolic flexibility, and execute cleanup efficiently. The body may therefore be overfed in caloric terms and underbuilt in functional terms. This is one reason people can consume omega-3 supplements inside an otherwise inflammatory dietary structure and see only partial benefit. Resolution requires more than adding precursor. It requires a tissue environment able to preserve, convert, and act on that precursor. Barrier injury is another major pathway through which diet disrupts SPM production. Modern processed food patterns often destabilize the intestinal environment through emulsifiers, irritant food structures, repeated glycemic excess, low fiber patterns, poor bowel coordination, and altered microbial ecology. Once intestinal barrier integrity weakens, immune-provoking material continues reaching tissues that should have been allowed to quiet down. Endotoxin burden rises. Immune activation becomes easier to sustain. The liver and vascular system are exposed to repeated inflammatory traffic. Under those conditions, the body remains locked in repeated initiation. The enzymatic and cellular context required for mediator class switching toward pro-resolving output becomes harder to establish because the tissue never receives a convincing enough reduction in upstream provocation. SPM production is therefore disrupted not only by what the diet contains, but by the way the diet prevents the body from ever entering a stable enough state to prioritize completion. There is also a temporal problem built into modern eating patterns. Resolution biology depends on tissues having the opportunity to complete processes. Constant grazing, repeated exposure to hyperpalatable engineered foods, chronic caloric surplus, and the absence of meaningful metabolic quiet reduce the intervals in which the body can re-establish lower noise signaling conditions. The organism stays in a near-continuous state of digestive, endocrine, and inflammatory engagement. That does not mean eating itself is harmful. It means a food environment built around perpetual stimulation makes it harder for the body to finish one wave of physiological work before the next one begins. SPM production is impaired in that kind of system because resolution depends on clean transitions, and modern eating patterns often erase transitions altogether. The modern diet also alters tissue composition over long time horizons in a way that reinforces enzymatic bottlenecks. Cox and LOX pathways are shared, competitive, and context-dependent. In a tissue repeatedly loaded with omega-6 dominant membrane substrate and repeatedly activated by dietary inflammatory stress, those enzyme systems remain heavily occupied by initiation-heavy traffic. EPA and DHA are not absent in principle, but they enter a biochemical landscape already biased toward arachidonic acid-driven mediator production. That means the bottleneck is not just low intake of omega-3. It is low pathway influence of omega-3 inside a tissue whose enzymes are being asked, over and over again, to support early-phase inflammatory chemistry. Modern diet keeps the system practicing escalation, so when the moment for resolution arrives, the enzymatic landscape is still crowded with the habits of initiation. This is why the phrase anti-inflammatory diet is often too small to describe what is actually needed. The body does not simply need fewer inflammatory foods. It needs a dietary environment that reduces repeated re-triggering, protects membrane integrity, restores a more coherent omega-6 to omega-3 substrate relationship, supports mitochondrial capacity, strengthens barrier function, and allows phase transition into true inflammatory completion. In other words, the real dietary problem is not only that modern food creates more inflammatory signals. Is that it systematically dismantles the structural, energetic, and enzymatic conditions required for SPM biology to become effective enough to close inflammatory events once they have started. Seen clearly, modern diet disrupts SPM production by attacking the resolution program from every angle at once. It overbuilds initiation substrate, underbuilds omega-3, derived completion substrate, increases oxidative damage to the very membranes that must store that completion substrate, crowds enzymatic pathways with early-phase chemistry, keeps barriers leaky, keeps tissues metabolically noisy, and reduces the organism's opportunity to move from defense into repair. The result is a body that still knows how to inflame, but is progressively less capable of deriving the lipid mediators required to stop inflaming well. That is the deeper dietary problem. Modern food does not merely make inflammation more likely, it makes completion less available. Omega-6 dominance blocking pathways. Omega-6 dominance blocks pathways not because omega-6 is inherently illegitimate, but because enzymatic systems, membrane space, and inflammatory signaling capacity are finite. When tissues are repeatedly built from an environment saturated with omega-6 rich substrate, especially linoleic acid feeding the broader arachidonic acid-heavy signaling reservoir, the body does not simply store more fat. It changes which inflammatory language is easiest to generate. Membranes become more heavily stocked with substrate for early-phase eicosanoid production, and the shared enzymatic machinery that processes polyunsaturated fatty acids becomes increasingly occupied by the chemistry of initiation. In that setting, omega-3 derived substrate is not always absent, but is functionally outcompete. It has less room in the membrane, less relative access to the same conversion systems, and less downstream influence when inflammatory activation begins. The result is a body that is biochemically prepared to escalate faster than it is prepared to resolve. The first level of blockage happens at the level of membrane incorporation. EPA and DHA do not enter an empty membrane waiting to welcome them. They enter phospholipid pools already shaped by long-term dietary input, endogenous remodeling, oxidative turnover, and tissue-specific demand. If omega-6 input remains chronically dominant, more of the membrane reservoir is allocated to linoleic acid-derived and arachidonic acid-related structural potential, which means less relative space is available for EPA and DHA to become a meaningful fraction of the releasable substrate pool. This matters because inflammation later draws from what the membrane already contains. A tissue with omega-6 dominant phospholipid composition is preloaded for one kind of response. Even if omega-3 is later added, it may take time and significant remodeling to shift that stored ratio enough to change future mediator output in a biologically strong way. The second level of blockage happens at the level of shared enzymatic traffic. Omega-3 and omega-6 families are processed through overlapping elongase, desaturase, cyclooxygenase, and lipoxygenase systems. These pathways are not infinitely available. If a tissue is continually mobilizing arachidonic acid-heavy substrate and continually using COX and LOX pathways for early-phase inflammatory chemistry, EPA and DHA are forced to compete in an environment already organized around initiation. The issue is not that the enzymes refuse omega-3. The issue is that the biochemical road is crowded. Arachidonic acid is being released, converted, and used at scale, while omega-3 derived substrate remains relatively weaker in both abundance and pathway priority. Under those conditions, the body keeps generating the products it is best prepared to generate. Resolution pathways remain possible, but they are biochemically underpowered. The third level of blockage is phase dominance. A tissue rich in omega-6 derived inflammatory potential tends to remain more fluent in the front half of the inflammatory program. It enters initiation quickly, amplifies efficiently, and keeps those pathways active because the substrate environment supports them so well. That matters because specialized pro-resolving mediator generation is not just a question of substrate presence. It also depends on mediator class switching, the transition in which the tissue stops prioritizing escalation and begins prioritizing closure. Omega-6 dominance makes that switch harder because the inflammatory environment keeps reinforcing the earlier phase. The body remains chemically convinced that more recruitment, more permeability, and more eicosanoid-driven force are still useful. In that context, omega-3 derived resolution chemistry never gains enough influence to take command. This is why omega-6 dominance does more than increase inflammatory potential. It narrows inflammatory imagination. The tissue keeps solving problems with the same front-loaded chemistry because that is what the structural reservoir and enzymatic landscape are most prepared to produce. More prostaglandin and leukotriene logic becomes easier than more resolvin, protectin, and mycin logic. More neutrophil recruitment becomes easier than more macrophage-led cleanup efficiency. More pain sensitization becomes easier than more withdrawal of pain once tissue protection is no longer needed. In practical terms, omega-6 dominance blocks pathways by making the body repeatedly choose the inflammatory entrance and struggle to find the biochemical exit. This does not mean the solution is to eliminate omega-6 completely. The body still needs initiation chemistry. It still needs arachidonic acid-derived signaling for acute vascular response, immune recruitment, and tissue defense. The real problem is disproportion. When omega-6 derived substrate so heavily outweighs omega-3 derived substrate that membrane composition, enzymatic throughput, and tissue timing all become biased toward escalation, the resolution phase becomes chronically undersupported. The body still inflames efficiently, but it no longer resolves with comparable strength. That is what pathway blocking really means here. Not absolute inhibition, but structural and enzymatic crowding that makes the chemistry of completion too weak relative to the chemistry of initiation. Seen clearly, omega-6 dominance blocks pathways by controlling all the upstream conditions that decide what inflammation can become. It occupies membrane real estate, competes for shared enzymes, reinforces mediator patterns that favor early phase activity, and makes the shift into resolution less likely to gain dominance once inflammation is underway. The tissue does not become doomed, but it does become biased. It starts more easily than it finishes. That is the real consequence of omega-6 excess in a modern inflammatory environment. It does not just add more fuel to inflammation. It makes the body less able to access the roads required to bring inflammation to an intelligent end. Substrate competition. Substrate competition is one of the central reasons omega-3 and omega-6 cannot be understood as isolated nutrients acting independently inside the body. They share space, they share enzymes, and they compete for influence at the exact points where structure becomes signaling. This competition begins long before a mediator is formed. It begins at incorporation into membranes, continues through storage in phospholipids, persists at the moment of phospholipase release during inflammatory activation, and then intensifies again when cyclooxygenase and lipoxygenase enzymes begin converting available fatty acids into downstream lipid mediators. The body is not choosing between abstract categories. It is working with whichever substrates are most available, best positioned, and most dominant within the membrane environment at the moment the inflammatory sequence is triggered. That means tissue behavior is not determined by the existence of omega-3 or omega-6 in principle. It is determined by their competition in practice. The first arena of substrate competition is the membrane itself. Phospholipids can only hold so many fatty acids, and those positions matter because they become the reservoir from which later inflammatory and pro-resolving mediators are derived. If tissue is built in a context of chronic omega-6 dominance, then more of those phospholipid pools become enriched with linoleic acid-derived and arachidonic acid-related substrate, while EPA and DHA remain relatively underrepresented. When inflammatory activation later occurs, the body can only release what it previously stored. A tissue rich in omega-6 substrate will therefore tend to release more of the material needed for early-phase eicosanoid production. A tissue richer in EPA and DHA will carry more of the substrate needed to support later pro-resolving mediator generation. This is not theory layered on top of the membrane. It is the direct consequence of what the membrane is made from. The second arena is enzymatic competition. Once phospholipids liberate fatty acids from membrane phospholipids, those fatty acids enter shared processing systems. Cyclooxygenases and lipoxygenases do not belong to one fatty acid family alone. They handle whichever substrate reaches them under the conditions present in that tissue. If arachidonic acid is abundant and repeatedly mobilized, those pathways will tend to generate arachidonic acid-derived eicosanoids that support initiation, amplification, vascular change, pain sensitization, and immune recruitment. If EPA and DHA are more meaningfully present and the tissue has shifted far enough into the later phase of inflammatory sequencing, then the same broad mediator landscape can begin moving toward resolvins, protectins, marazins, and other products more associated with completion. The point is not that one pathway exists and the other does not. The point is that they are competing for throughput. The body generates more of what its substrate environment most strongly favors. This competition also changes how inflammation feels and behaves at the tissue level. A membrane dominated by omega-6 derived releasable substrate does not only produce more early-phase mediator potential, it changes the probabilities of what an activated cell will do next. More substrate for arachidonic acid-heavy eicosanoid cascades means stronger bias toward recruitment, permeability, and inflammatory escalation. More EPA and DHA in the membrane does not automatically erase that, but it does create the possibility for different downstream mediator output and a stronger foundation for later class switching into resolution biology. In this sense, substrate competition is not only about quantity, it is about direction. The body can begin an inflammatory event from several possible biochemical landscapes, and whichever substrate pool dominates will influence whether the tissue moves more easily toward sustained activation or toward timely completion. Timing makes this even more important. Early in inflammation, the body often draws heavily on whatever substrate is most readily available for fast local signaling, and chronic dietary patterns determine what that available pool looks like before the acute event even begins. This means the inflammatory sequence is partly written in advance. If a tissue has been built over months or years under conditions of omega-6 excess and weak omega-3 incorporation, the competition has already been tilted before the first neutrophil arrives. When the trigger occurs, the body reaches into the reservoir it has. That is why substrate competition is such a powerful explanation for chronic inflammatory bias. The organism is not making inflammatory decisions from scratch in every moment. It is making them from a structural memory stored in membrane. Substrate competition also helps explain why simply adding omega-3 sometimes produces gradual or incomplete change. EPA and DHA must do more than appear in circulation. They must displace or meaningfully counterbalance existing membrane composition, survive oxidative conditions long enough to remain useful, and exert enough influence within shared enzymatic systems that the body's downstream mediator profile begins to shift. In a tissue long dominated by omega-6 derived substrate that is not instantaneous, the membrane has to remodel. The releasable pool has to change. Enzymatic traffic has to become less crowded by early-phase chemistry. The inflammatory environment has to move far enough toward resolution that omega-3 derived substrate can express more than a minor downstream effect. Until then, the competition remains structurally biased, and the body continues speaking mostly in the older inflammatory language. Seen clearly, substrate competition is one of the most important hidden rules of lipid biology. It explains why the body can require both omega-3 and omega-6 while still being harmed by disproportion between them. It explains why membrane composition matters so much before symptoms appear. It explains why chronic inflammatory states often feel chemically locked into escalation. And it explains why the path to stronger SPM biology is not merely about supplement intake, but about changing the actual substrate environment from which inflammation and resolution are both built. The body resolves from the materials it has on hand. If those materials are too heavily weighted toward initiation, then competition itself becomes part of the reason the body keeps starting more easily than it finishes. Oxidative damage to PUFAs. Polyunsaturated fatty acids are biologically powerful because their multiple double bonds make them flexible, dynamic, and useful as both membrane components and signaling substrates. But those same double bonds also make them chemically vulnerable. This is the core problem of oxidative damage to PUFAs. The very structural feature that allows omega-3 and omega-6 fatty acids to participate in membrane fluidity, receptor environment, and downstream mediator generation also makes them easier targets for free radical attack and lipid peroxidation. A polyunsaturated membrane is not just a signaling-capable membrane. It is also a membrane carrying built-in fragility if the surrounding environment cannot protect it. That fragility matters because once peroxidation begins, the tissue does not simply lose a few fatty acids. It begins to lose structural coherence, signal precision, and the integrity of the very substrate pool from which both inflammatory and pro-resolving mediators are supposed to be generated. This is especially important in a modern inflammatory environment where oxidative stress is not a rare event but repeated condition. Mitochondrial inefficiency, chronic immune activation, glycemic volatility, endotoxin exposure, endothelial irritation, environmental toxins, poor antioxidant capacity, and repeated tissue injury all increase the likelihood that membrane PUFAs will be exposed to reactive oxygen species and related chemical stress. When that happens, polyunsaturated fatty acids are prone to peroxidative chain reactions. One attacked lipid can destabilize neighboring lipids, creating a spreading zone of membrane injury rather than an isolated molecular event. The result is not just chemical damage in the abstract. Membrane permeability can change. Receptor behavior can distort. Ion gradients become harder to maintain. Signaling becomes noisier. The tissue begins making decisions through damaged surfaces. This problem has a special relevance for omega-3 biology because EPA and DHA are among the most unsaturated fatty acids in human membranes. They are therefore highly valuable as resolution substrate and highly vulnerable as oxidative targets. That combination creates one of the central tensions of this book. The body needs these fatty acids because they provide the precursor pool for resolvins, protectins, and maresins. But if the tissue environment is heavily oxidized, those same fatty acids may be damaged before they can be preserved, released, and converted into useful pro-resolving mediators. In that setting, the issue is not that omega-3 is bad. The issue is that highly unsaturated substrate placed into an unstable oxidative environment becomes fragile. The membrane is carrying the material for resolution, but the chemistry of the surrounding tissue keeps injuring that material faster than it can be used intelligently. This has consequences at both the structural and signaling levels. Structurally, peroxidized PUFAs destabilize the membrane. They alter packing behavior, disrupt local protein environments, increase the likelihood of leakiness or altered receptor function, and contribute to the breakdown of the carefully organized surface conditions on which signaling depends. Signaling-wise, oxidation of PUFAs distorts the substrate pool itself. The body no longer has the same reservoir of clean, usable fatty acids available for enzymatic conversion into controlled mediator families. Instead, it accumulates reactive byproducts, including aldehydes and oxidized lipid fragments that can act as damage signals, interfere with proteins, injure nearby structures, and prolong inflammatory interpretation of the tissue. A membrane that should have been a reservoir for orderly mediator generation becomes a source of biochemical noise. This is one reason oxidative damage to PUFAs contributes directly to failed resolution. A tissue cannot generate strong, clean pro-resolving output if its omega-3 derived substrate is being chemically degraded or if its membranes are so oxidatively unstable that they continue releasing distress chemistry faster than they can support class switching into completion. The tissue remains in a chemically ambiguous state. It carries enough PUFA content to be vulnerable, but not enough protected PUFA integrity to use that content well. Instead of moving from initiation toward resolution, the body keeps encountering oxidized lipid evidence that tells it damage is ongoing. Inflammatory signaling, therefore, remains justified. The site stays open, reactive, and incomplete. Oxidative damage also makes substrate competition worse. In a tissue already dominated by omega-6, heavy initiation chemistry, damaged omega-3 derived substrate loses even more of its downstream influence. Not only is EPA and DHA underrepresented relative to arachidonic acid in many modern membrane environments, but whatever omega-3 is present may be more vulnerable to oxidative attrition if the tissue remains metabolically noisy. That means the body does not just suffer from poor omega-3 incorporation. It suffers from poor omega-3 preservation. The result is a double loss. Resolution substrate remains relatively sparse, and the portion that does arrive is less stable than it should be. Under those conditions, the balance of inflammatory chemistry tilts even more strongly toward escalation. Seen clearly, oxidative damage to PUFAs helps explain why simply increasing intake of polyunsaturated fats, even beneficial ones, does not automatically improve tissue behavior. The question is not only whether the body contains enough EPA, DHA, or other PUFAs. The question is whether the body can protect them well enough to use them as intended. A well-supported membrane can hold polyunsaturated structure and later convert it into useful signaling. A poorly protected membrane turns that same structure into a liability. This is why membrane stability, antioxidant sufficiency, mitochondrial control, and reduction of repeated inflammatory stress are all part of the same story. The body does not resolve from fragile substrate very well. It resolves from substrate that remains intact long enough to be converted into the chemistry of completion rather than the chemistry of ongoing damage. Loss of resolution capacity. Loss of resolution capacity is what happens when the body still retains the machinery to begin inflammation but no longer retains enough structural, signaling, and energetic competence to bring that inflammation to a proper end. This is one of the most important turning points in chronic disease because it marks the shift from useful inflammatory responses to repeated unfinished ones. The body can still detect disruption. It can still mobilize arachidonic acid, generate eicosanoids, recruit neutrophils, alter vascular permeability, amplify pain, and activate immune defenses. In that sense, force remains available. What is being lost is not inflammatory power. What is being lost is the ability to transition that power into cleanup, restoration, and closure. The tissue stops being good at finishing. That loss can develop gradually. Membranes become more enriched in omega-6, dominant activation substrate, and less effectively enriched in EPA and DHA. Whatever omega-3 derived substrate does enter the membrane may be more vulnerable to oxidative damage because the surrounding environment is increasingly unstable. Shared enzymatic pathways remain crowded with initiation-heavy traffic. Specialized pro-resolving mediator production becomes too weak relative to the scale of inflammatory activation. Macrophages become less effective finishers, either because their phenotype remains too inflammatory, because cleanup demand exceeds their capacity, or because the tissue environment never shifts far enough into the later phase to support efficient erythrocytosis and repair. Barriers stay open. Mitochondrial output stays strained. In that setting, the body does not lose resolution all at once. It loses it by attrition. Each inflammatory event becomes a little harder to close than the one before it. The practical consequence is that tissue begins carrying forward the residue of previous inflammatory cycles. Apoptotic cells are not removed fast enough. Oxidized lipid fragments remain in place. Damaged membrane material continues, signaling danger. Endothelial and epithelial surfaces fail to re-establish full control. Pain signaling remains amplified because the local environment still looks unsafe. Immune cells continue encountering evidence that the job is unfinished, so the body stays ready to reinitiate. This is what loss of resolution capacity really means. It means the site never becomes convincingly complete enough for the organism to stand down. Inflammation keeps recurring not necessarily because the original trigger is still large, but because the tissue still carries unresolved evidence of that trigger and the damage that followed it. This is why chronic inflammatory states often feel self-sustaining. Once resolution capacity is sufficiently weakened, each new inflammatory event does more than create an immediate burden. It also worsens the tissue's future ability to resolve the next one. More oxidative damage weakens membrane integrity further. More uncleared debris increases future inflammatory signaling. More mitochondrial strain reduces energy available for later repair. More barrier dysfunction increases the probability of repeated provocation. The body becomes trapped in a compounding loop. It still knows how to start, but every cycle leaves it slightly less able to stop well. The problem is no longer only what is triggering inflammation. The problem is that the organism is losing the internal capacity required to complete inflammation as a program. Seen clearly, loss of resolution capacity is one of the deepest ways to describe chronic illness. It explains why symptoms persist after the apparent trigger should have passed. It explains why tissues remain reactive, painful, permeable, and metabolically expensive. It explains why simply reducing inflammatory intensity often fails to restore true baseline. Most importantly, it explains why modern health problems so often involve not a failure of defense, but a failure of closure. The body is still trying to protect itself. It has simply become less able to finish that protection without remaining trapped inside it.